then and there do you need for Calc 1. So, all right. Okay, we're looking at inverse trig functions today. For inverse trig functions, this is going to be the way that we solve trig equations, sort of. Whenever we think about inverses, we switch our x and our y's, and then we solve for that new y. So I have used inverse trig a few times whenever we need to find an angle. And there are two types of notation that you can use for this. The one you've probably seen the most right here is something like this, sign with a little -1 right here. Now, Mr. Passwater says that we call either one of these arc sign. I usually don't do that. I usually call it inverse sign a lot of times. But you will see some textbooks and some things that are published that use this notation instead, arc sign, and apparently Mr. Passwater calls it arc sign even if it's written as sign to the -1 power. I have not been in the habit of doing that, but it could be done that way for sure. But these two types of notation are interchangeable. It does not matter whether something says inverse sign or arc sign. It is the same thing. And I need to look through the released material to see. I think either one of them is fair game for the AP Calculus, AP Precal exam. But I think they tend to use the inverse notation a little bit more. It's good for you to know both of those notations because soon you will be headed off to colleges where you will be taught by professors. Some of them may have been teaching a math class for 40 years, and if they learned at arc sign, there's a good chance they have not changed their ways. So it's good to, be able to adjust to whatever you see, because they are both accurate notation that you can use. The statement sine of pi over 6 equals 1/2 is an equivalent form of using arc sign notation. So whenever we look at this, if I want to write this using arc sign notation, I know, and this is just a unit circle value, if I find sine of pi over 6, I would go to pi over 6, I would look at my y coordinate, it would be 1/2, right? So this is a true statement. If I want to rewrite this with inverse sign notation, I would do inverse sine of both sides, and then I would have pi over 6 equals arc sign. I want to be like Mr. Passwater because he is my hero for making all of these worksheets for me. Then it would be written like this. You also could see something like this. Arc sign of 1/2 equals pi over 6. So when you see arc sign or inverse sign notation, what it's really asking right here is where does sine of theta equal 1/2? That, when you see arc sign notation, it's saying where, what angle does sine have this value? Or it could be cosine or it could be tangent. We'll see as well for this. Now, whenever we look at trig functions and think about their inverses, the trig functions are certainly functions. They pass a vertical line test. Each x only has one y. But these values are repetitive, right? So like if I think about just making a table for sine, if I've got x and sine x, if I got 0, pi over 2, pi, 3 pi over 2, 2 pi. and then I'm going to go 5 pi over 2 just to have one extra right here. If I make a table for this, sine of 0 is 0, sine of pi over 2 is 1, sine of pi is back to 0, sine of negative 3 pi over 2 is negative 1, back to 0, back to positive 1, right here. So this is a function. This is fine. Every x has a different y. But whenever I graph the inverse, I got to switch my x and y's, right? So I'd have 0, 0, 1 pi over 2, 0 pi, negative 1, 3 pi over 2, 0, 2 pi, 1, 5 pi over 2. Okay. Now, is that new table, is it a function? Is it, for a function, each x can only have one y. But right here, when my x is 0, I got 3 different places where x is 0. Do I have the same y every time for that? I do not. I've got different y's. So with x's repeated, you can't have a function, right? So if I were to just switch my x's and y's on the sine function, my result is not a function. It could still be a relation, but it's not a function. So in order to have an inverse sine function, we have to restrict the domains so that we don't have repeated y values. So for sine, what we do here is we're going to look at negative pi over 2 to pi over 2. Because for sine, no y values will be repeated in that interval right there. Now, if I went further, if I went all the way over here to pi, y values start to be repeated because I'm going back down and catching some of those values again for that. So for sine, we're going to restrict the domain to negative pi over 2 to pi over 2. For cosine, it's going to be different because if I went from negative pi over 2 to pi over 2 on cosine, I would have repeated y values up there in that top part, and I'd be missing the whole bottom part. Like I wouldn't have any negative values. So I would not do the same values for sine. For cosine, we are going to restrict our domain from 0 to pi. So that it will be a function, yes. And for tangent, due to your vertical asymptotes, if we think about that tangent graph we were just looking at yesterday, I had vertical asymptotes at negative pi over 2 and pi over 2, and no y values were repeated in between those. So from negative pi over 2 to pi over 2 can be our restriction for that as well. So sine and tangent, sometimes these are called principal values. Sine, I should write that down because when we get to solve an equation, sometimes it might say to solve for principal values. So these are our principal values here. So for sine, it's negative pi over 2 to pi over 2. For tangent, it's negative pi over 2 to pi over 2. For cosine, it's 0 to pi. Now, we're not going to get out our calculators, but your calculator automatically does this. So whenever Desmos or either for Desmos or for the actual graphing calculator, if I type in cosine inverse of 1, I get 0. If I type in cosine inverse of 1/2, I get 1.047, which is going to be pi over 3, right? For that. When you type inverse cosine into a calculator, it's only going to give you one value. But if you think about that unit circle, there's lots of places that cosine equals 1/2, right? You got 2 places that are on the unit circle. You've got at pi over 3 and 5 pi over 3. Your x-coordinate is 1/2. And then you could spin around a bunch of times, and those would be, you'd actually have infinite answers for that. So, so the calculator is automatically restricting these domains to those sections every time. Questions? All right. So, if we are asked to evaluate these here, I am going to think about my unit circle for each one of these. When we see cosine inverse of negative root 2 over 2, it's really asking, where does cosine of theta equal negative root 2 over 2? So if I think about my unit circle here, cosine is my x-coordinate. Right here, I get negative root 2 over 2, and the y-coordinate is positive root 2 over 2. Right down here, I would also get negative root 2 over 2 and negative root 2 over 2. So I've got both of these places, which is 3 pi over 4 and 5 pi over 4. But for cosine, I have to restrict my domain. Where's the only place I look for cosine? 0 to pi, top half. So oh gosh, it messed up my picture here. I really only need to look at this point right here because I'm only looking at the top half of the function. So the answer that you're given is the angle where that occurs, which is 3 pi over 4. Okay. So B is asking me, where does sine equal negative root 2 over 2? Now for sine, I only care about the first and the fourth quadrant, and there's going to be a little something different we got to do if it ends up being in that fourth quadrant. So for sine, I would only be looking for answers over here in that first or the fourth quadrant. And so sine, I know it's my y-coordinate, and I'm going to put my first quadrant first. I know this point right here at pi over 3 would be 1/2 root 3 over 2. That's not it because it's not negative, but whenever I graph that corresponding point down here, which this one is 5 pi over 3, I would have 1/2 negative root 3 over 2. So right here is where I'm looking for my answer. But is 5 pi over 3 between negative pi over 2 and positive pi over 2? It is not. So if your answer is in the fourth quadrant here, you have to do negative angles. So rather than calling that 5 pi over 3, because 5 pi over 3, like if you multiply that together, if you get the decimal, it is not between negative pi over 2 and pi over 2. Let me just pull up Desmos over here so we're all very clear on that. Pi over 2 is 1.57. Negative pi over 2 is the same but negative. If I do 5 pi over 3, that's 5.23. It's not between those two numbers, right? So I've got to use negative values for this, which means that I'm going to call that negative pi over 3 instead of calling it 5 pi over 3. I'm going to make that negative look a little better. What? You have to give, when you're doing inverse sine, you have to give the answer from that restricted domain. So for sine, that is from negative pi over 2 to positive pi over 2. That piece of that graph that you're supposed to look at right there, where the y values don't repeat, is from negative pi over 2 to pi over 2. So 5 pi over 3 does not fall between those numbers. That's going to be like negative 1.57 up to positive 1.57, and 5 pi over 3 is like 5 point something. So negative pi over 3. I'll go back over here to Desmos. It's fine though. Negative pi over 3 is like negative 1.047. So it is between negative 1.57 and positive 1.57. There. So basically, anytime your answer ends up being in the fourth quadrant for a problem like this, you're going to need to use negative angles instead of using those values we know from the unit circle.
So is the negative angle just the other possibility of the answer?
Do you mean like it corresponds to the like pi over 3 up in the first quadrant? Yeah, because it's that same distance away, but it's in the clockwise direction. Yes. Yes, if it's in the fourth quadrant for tangent, because tangent has those same restrictions as sine, you will do the same thing there. So anything that comes from the fourth quadrant when you're doing inverse trig, you're going to change those to negative angle values instead of using the angle values that are on the unit circle. All right, so let's look at tangent, because tangent is harder, because tangent values are not on the unit circle. All right, so for tangent, first of all, for tangent, just like with sine, I only want to look in first and fourth quadrant, because this would be negative pi over 2 all the way up here to positive pi over 2. Now, tangent values are not on the unit circle. I can tell if this is going to be in the first quadrant or the fourth quadrant, because I know up here both sine and cosine are positive. Down here, cosine is positive, but sine is negative. What's the sign of tangent going to be in that fourth quadrant? It's going to be negative, so it's not the answer, right? So I don't have to worry about those. I know it's got to be one of the places where I have a square root of 3, but unless you've really, really memorized the unit circle and all of its values really well, it's probably going to be hard for you to tell whether it is square root of 3 over 2, 1/2, or 1/2 square root of 3 over 2. I know it's got to be one of those two because it has a square root of 3, and that's where it came from. So what I usually do is I just test it. So I'm going to do tangent of pi over 6, which is sine, which is 1/2, over cosine, which is square root of 3 over 2. And dividing fractions is easy as pie. Flip the second and multiply. My 2's cancel, but I'm going to get 1 over the square root of 3, which I'd have to rationalize. That would be square root of 3 over 3 right there. That is not it. So by process of elimination, I could go ahead and say that it's going to be pi over 3 for my answer there, because I know it's got to be one of those 2 points. But just to show you why it works out, tangent of pi over 3 is going to be square root of 3 over 2 over 1/2, which is going to be square root of 3 over 2 times 2 over 1. 2's cancel. You just get the square root of 3 there. It's not a bad thing to memorize what your tangent values are for those, but I seem to forget them even as long as I've been doing this, so I just work it out to the side. There. All right, we got one more kind of like weird kind of problem. AP likes to throw this stuff in here. Very theoretical. We have the angle theta is in standard position. So this angle right here is the angle theta. The terminal ray intersects the unit circle at point P, whose coordinates are x, y. The points Q, R, and S are the result of the terminal ray being reflected over the y-axis, the origin, and the x-axis respectively. For which of the following expressions determine which point labeled intersects the terminal ray of the given angles? All right, so what I need is I need the coordinates of all these points. So this point is x, y. What would the coordinates of Q be? Negative x, y. What are the coordinates of R? Negative x, negative y. And what are the coordinates of S? X, negative y. Right there. Alright, so when I have a question that says cosine inverse of x, what it's asking me is where does cosine of theta equal x? Alright, cosine is your x coordinate. Okay, where does cosine equal x? Which points? Because it's cosine inverse. Yeah, this is not a multiple choice question. Yeah. So where does cosine of theta equal x? Not 2 and 3. It's 1 and 4. Because you're just looking for where cosine is your x coordinate, right? You're looking for where that x coordinate is just x, right? And so this doesn't ask us for the angle because it didn't give us the angle. It just says give the labeled point for that. So our answer here would be P and S. Okay, so whenever we see B, it's saying where does sine of theta equal negative y? What points is that one going to be? R and S. So C is saying where does cosine equal negative x? What are our points going to be for that one? Q and R. Last one's the trickiest because tangent's not on the circle. Where does tangent of theta equal negative y over x? At Q, because we would do sine over cosine, which would be y over negative x, which would be negative y over x, and also at S, negative y divided by x there as well. Okay, does that make sense? Okay, it seems a little much to wrap your head around, but once you look at it, it's just asking you where you have those values. All right, so we're going to take we should do 9 right here. All right, so this is a lot of inverse stuff going on here on number 9. But we want to start with this part right here because this is a value. Okay, this is asking me where does sine of theta equal negative root 2 over 2. So if I'm thinking about that unit circle for sine, I only look at the first and fourth quadrant. I would have to have this point right here. That's where I'm going to get positive root 2 over 2, negative root 2 over 2. What would I call that angle right there? It is negative pi over 4. It is also going to be 7 pi over 4 on your unit circle, but we have to use negative angles when we're in that first quadrant. So this whole thing right here, it's asking me where does sine of theta equal negative root 2 over 2, and it equals negative root 2 over 2 at negative pi over 4. All right, so what I'm trying to do here is I'm trying to solve for that x right there. So the next thing I've got to try to get rid of over here is that inverse tangent. How would I get rid of an inverse tangent? Just regular tangent. So if I do tangent of this side, it'll cancel that out, and I'll just have pi times x. And over here, I'll be doing tangent of negative pi over 4. So tangent of negative pi over 4 is not on the unit circle, because tangent is not on the unit circle. But how do I find tangent of negative pi over 4? Y over x. So I will have negative square root of 2 over 2 divided by positive square root of 2 over 2. And that is just going to give me negative 1. And then, I'm trying to get that x by itself. What do I need to do? Divide by pi. So, x equals negative 1 over pi. That's my answer for that. So, all of these, you'll notice, like that first step that I did, all of these have an inverse cosine something that is a value you can find. So that's where you want to start on all those problems. You want to find that first and then solve the equation for the x. And to get rid of an inverse sine or cosine or tangent, you just use that function itself. Okay. All right. So keep all of them. That's okay. All right, so for 1, you should get pi over 3. 2 is negative pi over 4. 3 is pi over 4. 4 is 5 pi over 3. I'm sorry, 5 pi over 6. 5 is negative pi over 6, and 6 is negative pi over 6. Okay, for 7, you should get 1. 8, you're going to get square root of 3 over 2. 9 we did together. 10, you're going to get square root of 3. On the back side, A is P, B is Q, C is S, Oh, you know what I did wrong earlier? I was given all the answers for all of the quadrants, but I should have restricted it. So I did that wrong on this. And so if you restrict it for sine, it should only be first and fourth quadrant, and it ends up being P for that. So if you have an extra one, that's my fault. I did that wrong whenever I did the notes. I should have restricted it and threw out some of my answers. For cosine, you should only look at first and second quadrant, so Q should be the only answer there. And tangent, you should only look at first and second quadrant, so you should only get S.
So every time they should only be 1.
Yeah, I wasn't thinking on that because inverse trig is restricted. I was thinking of it more like an equation, which is not right for that. So that is my fault. And then for A is S, B is Q, C is P. Oh, there is, sorry. D is P, E is P, and F is S. And you probably had more than one answer for some of those because I forgot to restrict. But the one that's not really the answer is not in the quadrant. Really, R should never be an answer because it's in the third quadrant. None of those answers ever come from the third quadrant. Okay. Let me pull this up. Let's start on... Okay, So let's talk about the equation that he has here, sine of x equals 1/2, and the equation sine inverse of 1/2 equals x. These two are related, but they're not necessarily equivalent because this sine inverse has a restricted domain. But we got lots of places where sine x equals 1/2, right? So depending on the context of the problem, sometimes you might want multiple answers. So what we're going to be seeing today is we're going to be solving trig equations, but we're either not going to have a restriction for answers, or we're going to be restricted just to the unit circle for that. Because you can see sine equals 1/2 at both pi over 6, so that would be an answer, and at 5 pi over 6. So if we're looking at the whole unit circle, we would get those two answers. But sometimes they don't even tell you to restrict it to the unit circle. Sometimes they ask for the general solution. So like if I took pi over 6 and I added 2 pi, I would get 13 pi over 6. There's another answer for this question. Or if I took 5 pi over 6 and I added 2 pi, 17 pi over 6, another answer. So you get these like basically infinite answers, right? Because you could add or subtract 2 pi an infinite number of times. So we're going to be doing very, very basic equations today, but we're going to look at how to give a general solution or a solution for like the whole unit circle. Whenever we write the general solution, so this is when they don't give us any restrictions. We're looking for any possible answer. It's a lot like we did for our vertical asymptotes. If we have sine, you are going to find the unit circle values where sine equals 1/2. It is pi over 6 and it is 5 pi over 6. But you can go around 2 pi however many times you want. And you would still end back up at that same spot where sine is 1/2. So what we do to give that general solution is what we did the other day with our vertical asymptotes. We say 2 pi times k, where k is an integer. And that just tells us we can add or subtract the period however many times we want. So for sine or cosine, you're going to do that. How's it going to be different for tangent? The period is just 1 pi, right? So it still works pretty much the same, but we're just going to add pi times k. Also, since the period is just pi, we only really have to look at like half of the circle for that. You don't have to give all of those values for that. So let's look at finding some general solutions. So if I'm thinking about cosine of x equals negative root 2 over 2, right? I'm just thinking on my unit circle, where does cosine equal negative root 2 over 2? And on that unit circle, cosine is your x coordinate, and so it's going to happen right here. You'll have negative root 2 over 2 and positive root 2 over 2. And it's also going to happen in that third quadrant right there. You'll have negative root 2 over 2 and negative root 2 over 2 at those points. So this point is 3 pi over 4, so you get x equals 3 pi over 4. And this point right here is 5 pi over 4. So we get x equals 5 pi over 4. If they told us just to give unit circle answers, we would be done. But it says all solutions, and there are an infinite number of solutions. So what we're going to do is to each one of our answers from the unit circle, we're going to add 2 pi, which is the period for these functions, times k. And then we're going to tell that k is an integer.
You have to state that every time. Or is it like common?
Yes. I mean, if you leave it off on your homework, it's not going to be the end of the world. But, like, if it is a free response question, you need to state that. for it to be correct. If you just put a k and don't tell us what k is, then it wouldn't be correct for that. Correct, correct. And you can kind of think of solving this like you're using an inverse, but it wants all solutions that would make this true, so we don't want to restrict that domain for it. Okay? So for example 2, I'm looking for where sine is -1. Okay? Sine is my y coordinate. Sine equals -1 right here. Okay? Those coordinates there are 0, -1. It's -1 and +1 are the only two numbers that only happen once on the unit circle for your trig functions. So that only happens once on the unit circle. You can call that x equals 3 pi over 2. You also could call it -pi over 2. It does not matter. You don't need to do both in this case because it's just that same point. And we'll put plus 2 pi times k, and we'll just draw an arrow over here. K is still an integer.
If there's only one solution, why do you need the 2 pi?
So there's only one solution on the unit circle. But if you spin around like another full rotation, you end up back at that same point. So that plus 2 pi k covers that. It covers all of those like coterminal angles that might be positive angles or negative angles there. All right, tangent is just slightly different. You're looking for where tangent is 1 over the square root of 3. So tangent, you're looking for where we got 1 over square root of 3. You really only need to look at half of the circle for tangent because you cannot get negative values. It doesn't really matter whether you look at like first and second or first and fourth. Here, this is going to be first quadrant because those are positive. And, you know, these are a little trickier to figure out because you've got like right here, you've got root 3 over 2, 1/2, and 1/2 root 3 over 2. But if I do sine, which is 1/2 divided by cosine root 3 over 2 here, dividing fractions is easy as pie. I'm going to flip the second and multiply. 2's cancel. I get 1 over root 3. That was for this point right here, which is at pi over 6. And the period for tangent is only pi. It's not 2 pi. So I'm going to do plus pi times k. And again, k is still an integer there for that. So